Okay, we started talking about acids and base last week, but we're going to finish it right here. So when we talk about acids and bases, we're actually talking about the pH scale. The pH scale, to make life really simple, if the situation becomes more acidic, the pH number drops. If it becomes more basic, the pH rises. And this is all because of a math scientist kind of guy that wanted to make life complicated, I swear, for students. But what happens is that the more free acid you have in a solution, the lower the pH is. The less free acid you have in a solution, the higher the pH. When you look at this scale, it goes from 0 to 14. 0 being the most acidic, 14 being the least acidic. Right in the middle, perfectly even, is neutral, which means that there's the same amount of acids as there are bases in the solution. So water, perfectly neutral water, distilled water that's just H2O, nothing else in it, sits at neutral pH of 7.0. If you split that, you actually have an H+, which is an acid, and an OH-, which is a base. So when you put them together, you neutralize them, turn it into water. When you look at some of the situations in the body, like gastric juice, the pH of 2 is way down here on the scale, so it's extremely acidic. When you take something like milk of magnesia, the reason you're doing this is because you're trying to neutralize some of these acids. You're bringing it back towards neutral. So what you really want to remember as a rule of thumb is the lower the pH number, the more free acids there are. When we label an acid, we refer to acids as hydrogen donors, electron donors, or H+ donors. I think I mentioned this in class. When I see this hydrogen, hydrogen's the first number on the periodic table. The only thing it owns in this whole world is one little electron. And electrons are negative. If you take away its electron, it has nothing. It gets really angry. It has a positive charge because it lost its negative. So this hydrogen with this positive charge is very destructive, very angry. It wants to go around inflicting damage on other things, is the way I think of it. The more of these free hydrogens you have, hydrogen ions you have, the more destructive the situation is. So it's like having a whole army of hydrogens out there looking for their teddy bears, and they just get really destructive and try and break things apart. Like proteins, when we talk about the GI tract, or when we did in physiology, these proteins in the stomach are being broken apart by acid, or actually denatured by acids. Bases accept those hydrogen ions. In other words, the bases, they have an extra electron on them, which makes them slightly negative. Since the electron is negative, it donates a little negative charge. So we have this hydroxyl group, which has a negative charge. When it bumps into this hydrogen that's looking for an electron, they neutralize each other. So they complement each other and they neutralize each other. That's why when you introduce an acid to a base, they have a tendency to neutralize. Right, when you look at acids or describe them, you can describe them as strong and weak. Strong acids, they dissociate. They come apart real easy. So if you take something like hydrochloric acid, which is HCl right here, the chloride wants to hang on to the electron and it steals it from the hydrogen. So when they get put in water, the hydrogen splits very easily. It's pulled away from the chloride and it loses its electron really easily, so it's very, very angry. In the stomach, you look at hydrochloric acid. When it's introduced to water in the stomach, it breaks apart, and that acid becomes very destructive and it tries to denature or uncurl proteins. This is sodium hydroxide. The Na, when you pull it apart, it has a positive charge, and it leaves the OH with a negative charge. The OH keeps the electron. So if I introduce this situation like NaOH to an HCl, since these are both very strong, they would actually neutralize each other. So if you remember from, if you've had chemistry or biology, or if you just remember talking about this in class before, if I take the H and the OH and I introduce them to each other, they make water, H2O. If I take the Na that has a positive charge and introduce it to the Cl, what would it make? It makes sodium chloride, table salt. So they have a tendency to neutralize each other too. But these things dissociate very easily. You put them in water and they start breaking apart. Just think about table salt. When you sprinkle it in water and stir it a little bit, it breaks apart. That helps you remember it. Weak acids don't. Things like lactic acid, it's weak. If you get enough of it, it can still be dangerous, but it's actually kind of weak. And typically we associate lactic acid with muscle activity. So you're making lots of lactic acid because that glycolysis is not using oxygen. It's making very few ATP and it's kicking out this bad byproduct, lactic acid. The pH scale, when you look at it, it's a logarithmic scale. Every time you change the number by 1.0, you're actually increasing the acidity or decreasing the acidity by 10 times. So if I take normal blood pH, which is 7.4, and I take it from 7.4 down to 6.4, I've increased it by 10 times the acidity. So it has 10 times more acid in the 6.4 than it did in the 7.4. So just think about this. If I take you from 7 all the way down to 2, so remember the stomach pH is around 2, I would go from 7 to 6, which is 10 times, 6 to 5, which brings it up to 100 times, 5 to 4, 1,000, 4 to 3, 10,000, 3 to 2, 100,000 more times acidic. So your stomach acid is roughly 100,000 times more acidic than your blood is. And the same thing works true if you go the opposite direction, 7 to 8. So it's 10 times less acidic, or 10 times more basic. Right, so why does it matter? You have to think about enzymes are the key. When you have enzymes in this pH solution that gets more acidic, they don't want to work very well. It's just like in the stomach. You have the enzymes that break down proteins, pepsin. When pepsin is introduced in the stomach, it has to be at a pH around 2. If you take that and move it into the small intestine that has a pH around 8, it's not going to work anymore. So enzymes in your blood are the same way. If I take an enzyme in your blood that's normally working just fine at 7.4 and I introduce it to something that's like 6.8, it's a bad situation. Those enzymes stop working or slow down their function, which is going to make it hard for you to do things like carry oxygen or move nutrients or carry hormones or different things, because they're all carried on proteins. Right? Enzymes are proteins. You change the shape of a protein, you change its function. Right? Also, it can affect electrolytes, and we talked about this a little bit last week. Also affect hormones, I just mentioned that. And then you want to keep in mind that if the blood changes from 7.35 to 6.35, how many times more acidic does your blood become? 10 times. It's 10 times more acidy than it was before, which means that those enzymes aren't going to work. In fact, if your blood drops below 6.8, you're a goner. Okay, so how do we change pH in the body? The number one thing you want to think about is proteins. When you break down proteins, or even carbs for that matter, when you break down proteins, you free up a lot of acids. And in your physiology class, you probably talked about this. People that are on a high protein diet, like an Atkins diet, their blood's more acidic, which means their urine's going to be more acidic. And it's because of the breakdown product or metabolism of these proteins. Same thing happens with carbs and fats. And carbs and fats you want to pay attention to in like situations like diabetics. When diabetics don't have enough free glucose, they have to start taking protein and fat and turning it into a glucose-like product. And when it turns it into that product to use for energy, it releases acids, and they call them ketone acids. And those ketone acids, they're still acidic, so the more you have, the more dangerous this situation becomes, and we'll talk about that in just a few minutes. You want to keep the body's pH between 7.35 and 7.45, the blood pH. And it can flux. If you notice, the average in here is 7.4. When you look at the different types of blood, you can have systemic arteries or systemic veins. And you want to think about that gas that's traveling, not oxygen, but the other one. And if you took physiology with me, you probably remember me really pushing this or telling you, when you see a rise in CO2, you also see a rise in acids. So when you think about it, which would be more acidic? Would it be the systemic arteries or the systemic veins? Hopefully you're thinking systemic veins. When you raise the CO2 in the veins, remember less oxygen, more CO2, the acid levels are going up. So it's going to be closer to 7.35, more acidic. The arteries are going to have less CO2, which will make them more towards the 7.45. Right? And then the key players we're going to talk about, the lungs and the kidneys, are the major organs that are involved in keeping this regulation. And here's the absolute range between 6.8 and 7.8, and some books refer to it as 6.8 and 8.0. If you go down to 6.8, you're a goner. If you go up to 8.0, you're a goner. Your acid base has gone so far out of whack, your enzymes can't stay in balance. They can't work properly, and then you start dying. Right. When we talk about acids, we can also refer to them as being volatile and non-volatile. When you hear about volatile acids, these things can be turned into CO2 quickly, so hopefully you're thinking what organ would take care of a volatile acid. The lungs. You breathe them out. The volatile acids can be converted really quick into CO2 gas, and you blow them out. So if somebody's becoming a little bit too acidic, and it's because of a volatile acid, like carbonic acid, this situation here, they'll start breathing heavier, blow it out. Non-volatiles are things like sulfuric, phosphoric, a lot of things that are metabolites of other products like proteins. Those have to be cleared through the kidneys. So again, the lungs and the kidneys, the key players. When you look at how we control the changes in acids, we have things called buffer systems. So buffer systems, they can actually take an acid or a base and help neutralize them, help keep them in check. So if I have something like a protein, proteins are made out of amino acids, long chains of amino acids. So one side of it's going to be an amine, which is basic. The other side is going to be acidic, so that if an acid comes into the cell near one of these proteins, the acid will grab a hold of the base side and get neutralized. If a base comes into the cell, it's going to move over to the acidic side and get neutralized. So proteins are really cool or handy little buffer systems. They work really quick. We're going to talk about a couple of these that work really fast, within seconds. Then we'll talk about the physiological buffer systems. And these take a little bit longer, potentially minutes, hours, or even a whole day to fix. And these are going to revolve around the kidneys and the lungs. Right. First, the buffer systems. And I already mentioned this. Buffer systems, what they do is they help neutralize acids and bases. So usually they'll have like an acidic side or a basic side that grabs a hold of its counterpart. So the basic side wants to grab a loose acid, the acidic side wants to grab a base. Right. The first buffer system we're going to talk about is called the bicarbonate buffer system. This is the most important one in the body, and hence all the capital letters. When you look at this process, the bicarbonate buffer system, you want to think of CO2, carbonic acid, and water. If I take something like water and CO2, I can actually turn it into carbonic acid, and I can turn that into a free acid and bicarbonate. And bicarbonate, when you see it, remember, is going to be HCO3 negative. So just like this, HCO3 negative. Right? This is carbonic acid. It's a balance. The bicarbonate buffer system keeps this homeostasis of pH, so it's right at 7.4. If I start making too much CO2, it'll shift things over and make more bicarbonate. If I make too much bicarbonate, it'll shift things over and make it into CO2. It keeps it in check. If I start making too much CO2 and this gets heavy, you should be able to think of what organ in the body is going to help you clear that extra CO2 out. And right away, you should think the lungs. If you're thinking, how do I get rid of bicarbonate? Bicarbonate, typically, if I get too much of it, I can urinate it out. I can push it out in the kidneys and then into the urine. All right, phosphate buffer is the next one, and this is intracellular. It's within the cells, especially in the kidneys. And this helps neutralize acids. So you have this phosphate, and it grabs a hold of an acid. They stick together. Here you see the positive charge on the acid. Here you see the negative charge on the phosphate. When they grab together, it gets neutralized. Okay? This can carry through the kidneys, it can be transported, it can be moved around, and then it can actually break free. It can find a hydroxyl group, a base, plug together, and then form a water and convert it back to that phosphoric acid. So it's kind of a process or a system. The key here is you want to remember this, an intracellular buffer. It's inside the cells, so that it's protecting the cells. It's keeping their environment safe. And then protein buffers, also mostly intracellular. And one of the key ones is hemoglobin. So hemoglobin can actually bind up an acid or a base, hold on to it, and then transport it safely. So if I have something like this, oops, forgot the plus on the hydrogen, but here you have a hydrogen ion, you have a hemoglobin, they bind together, and then you have this bound structure that can carry or transport that dangerous acid, like from your tissues, your muscle, where you're exercising, that dangerous acid can be carried. It gets up to the lungs, finds the CO2, and then the CO2 can actually dissociate, pop off, and then you can breathe it out. The next group, these are slower. So the first ones were fast, within seconds. The respiratory mechanism, the second one's a lot slower because you have to breathe it out. It takes time to breathe moving things. And you want to remember this key here, volatile acids are what it primarily moves. Right? Not the fixed ones, not the non-volatile acids like lactic acid or sulfuric acid or phosphoric acid. Those have to be cleared by another organ, and hopefully you remember the other major organ, the kidneys. So when you think about this, if your blood becomes too acidic, what would you start doing with the respiratory system to fix the acidity? So hopefully you're thinking CO2 is associated with high acids, so you must be blowing it out. Right? So primarily blowing it out. People that become too acidic, like Diabetics, when they're going through diabetic ketone acidosis, their breathing is heavier because they're trying to blow out extra CO2. And before I move on, actually, the ketone acids, the ketone biases are non-volatile. They're hard to clear by the lungs. But what the lungs are doing is it's trying to keep a balance. It's getting rid of the CO2 so that the ketone acids aren't as dangerous anymore. Because if you take one acid, whether it's volatile or not volatile, with another acid, whether it's volatile or not volatile, you have two acids. If you can get rid of one of them in any way you can, then it brings down the level of acids. It makes you more neutral, brings you back to neutral. So that's respiratory. A little bit slower. Usually it takes minutes to potentially hours to fix. And then the kidneys are the slowest of all. And then to help you remember that, just think about it. What do you do more often? Breathe or urinate? So breathing's fast. You can clear things away really quickly. The kidneys are interesting because the kidneys can actually do a lot of different things. The kidneys can take CO2. They can stick the CO2 into a bicarbonate, and then they can actually urinate the bicarbonate out. So they have the capability of clearing CO2 differently, but they can still clear CO2. The kidneys can also excrete more acid. So if your body's too acidic, it can push more acid into the urine and get rid of the level of acids. The kidneys they can't bring more acid back in. That's the catch. They can get rid of bicarbonate. They can make and keep more bicarbonate. They can get rid of acids, but they can't make and keep more acids. So when we start talking about how you compensate or fix things, the kidneys will try and push out acids. They'll try and push out bases, or they can try and keep a base, bicarbonate. So if you're in a state of alkalosis, which means that you have too many bases, can you or can't you bring back in acids from the kidney? Think about it a second. If your blood is too basic, can your kidney bring back in more acid? No, it can't. So what can it do? If your blood's too basic, what can the kidney do to help reduce the number of bases? It can actually kick bases out. It can make bases and put them into your urine to lower the number of bases in your blood. Okay, and then I started talking about this before. The carbonic acid bicarbonate pair, here's this little pathway. You take CO2 plus water, you make carbonic acid. That carbonic acid dissociates very easily. So it falls apart into a free acid and a free base. And this is bicarbonate here. So remember, the bicarbonate, your kidneys can clear. The acid, your kidneys can clear. The CO2, your lungs primarily want to clear. But if your lungs aren't working properly, the extra CO2 in your blood can stick to extra water in your blood, turn into carbonic acid, go down to the kidneys, and the kidneys can urinate these things out. So it can start urinating out extra acids. Right? The ratio they refer to as 20-to-1. So the pH is 7.4, but when they talk about the ratio of acids to bases, they usually refer to 20 bases for every one acid, which, when I think about this, I kind of think of this teeter-totter structure. So if the bicarbonate is our base, and it takes 20 bicarbonates to neutralize one CO2 acid, I think of it as which is heavier, a pound of feathers or a pound of lead? They're the same. So whether you have a pound of feathers or a pound of lead, they're the same. The size is different. It's going to be a little tiny drop of lead, kind of like a little tiny drop of acid, very heavy or very powerful. A big pile of feathers would be like the bases. So if I want to change this, if I want to change this balance here, shifting it 20-to-1, I can remove bases or add bases. So I can remove stuff from the feather pile or add to the feather pile. Or I can remove or add acids. So the acid pile. And it can move this teeter-totter back and forth and back and forth. When you look at this situation, too little CO2. CO2 is referred to as referenced as an acid, or ability to make an acid. So if I have too little CO2, what becomes more powerful in my blood? Well, if I have too little CO2, I can automatically think I have too little acid, which means the base becomes more powerful. So this would be a state of alkalosis. Another thing that can cause exactly the same thing, alkalosis, is that if I have too much of the base. I could keep the acid exactly the same, but if I add too much base on this side of the teeter-totter, it throws it off balance. So you have to look from two perspectives. And same thing with acidosis. I can add too much acid, or I can lose too much base, and it causes acidosis. So when you look at the shift back and forth, you have to look at, what am I changing? Am I changing the acid? If I make too much acid, it's acidosis. If I make too little acid, it's alkalosis. Then I look at the base. If it's too much base, it's alkalosis. If it's too little base, it's acidosis, because the acid becomes more powerful. And again, you're bringing it back to this teeter-totter, keeping in perfect balance. And of course, the minute little changes that happen within seconds are because of those little tiny bicarbonate buffers, intracellular buffers like phosphate and proteins. Those are the seconds chemical buffers. When I'm looking at the next fastest, this is going to be the kidney or the lung. It's the lung. I blow out CO2. I can breathe a lot more than I urinate. And then if the lungs aren't doing it, not fixing things, then I look to the kidney as the last resort. Okay. There are other buffer systems. When you look at things like just the charge, if the acids are becoming overwhelming in my blood, I can actually exchange acids for potassium. So I can swap them around. I can put the acid inside the cell and bring the potassium out of the cell, or vice versa. And we kind of talked about that a little bit last week. Right. Arterial blood gases, when you look at this, what they usually do is they'll poke a radial or brachial artery, and then they'll take out a little sample of the blood. These are the three main values you want to look at. The first one is the pH. So in the arterial blood gas, you're looking at about 7.35. When you look at the CO2 level, it's about 35 to 45 millimeters of mercury. So this is referring to your pressure. And this capital P before a gas refers to partial pressure. And the third thing you're looking for is your HCO3, which is bicarbonate. And this is the base, remember? So what was this associated with? If this is associated with a base, this must be associated with an acid. So what situation would you have if you had too much CO2? You had way more CO2 than you needed, but this was normal. You would be acidic. Just the opposite, if this were way too low, but the bicarbonate were normal, you'd be too alkaline, so alkalosis. They also take the oxygen, but the oxygen doesn't really play a role in acid-base balance. So they look at things like the SaO2, which is a saturation of hemoglobin. You'll probably talk about that in other classes. But it's just talking about how much oxygen is in the blood, right? So that's taken to determine if they have hypoxemia. And remember, hypoxemia means low oxygen in the blood, right? Hypoxic is referring to in the tissue. Hypoxemia is referring to in the blood. Okay, so just a reminder, normal pH between 7.35 and 7.45. You can take that ABG and look at it. If it's acidosis, there's too much acid compared to the base. If it's alkalosis, there's too much base compared to the acid. Okay. So if it goes below 7.35, then it's acidic. Remember the pH scale, the lower the number, the more acidic. If it goes over 7.45, it's alkalosis. Remember, the higher the number, the more basic or alkaline. When we refer to the term compensation, it's if the body is trying to fix things, right? So if it's fixing things, it's referred to as complete compensation. Partial compensation means that the range still falls outside of normal, but the body's trying to do something. So again, you can look at, this is the graph from your book, but here's your 7.4. If it drops below, it's acidic. If it goes above, it's alkaline. Okay. There's two ways to make it alkaline. You can either lose acid or gain bases. There are two ways to make it acidic. You can either accumulate acids or you can lose bases. There are four terms for acidosis and alkalosis. So these first two are easy ones, because if it says respiratory, you should automatically know what the problem is. Respiratory is referring to the lungs. There's something weird going on with the lungs. If it's respiratory acidosis, the first thing you want to pay attention to is, what does the lung try to fix? Does it try to fix bicarbonate, or does it try to fix CO2? CO2. So if it's respiratory acidosis, do they have too little or too much CO2? Acidosis. You want to think too much acid. And when we talk about CO2, you want to bring it right back. Too much CO2 at the same time. So respiratory acidosis means that they're retaining too much CO2. What's their lung doing? Would they be breathing too much or breathing too little if they have too much CO2 accumulated inside their blood? They're breathing too little. They're probably shallow breathing, or maybe they have something wrong with their lungs, like emphysema, some kind of a respiratory problem, or they're not exchanging CO2 and oxygen properly. Alkalosis, they're probably breathing really quick. They're blowing lots of CO2 out. It's kind of like when you blow up a balloon, you're blowing lots of CO2 out, you're actually sliding into a state of alkalosis because you're losing CO2, but you should automatically think you're also losing too much acid. Right? So respiratory, you know it's a problem with the lungs. Metabolic, you'd think naturally it has to be a problem with the kidney. It could be a problem with the kidney, but it could be anything that's not the lungs. So if you are overworking muscles or making the muscles too active, way too fast, of course you're going to start breathing and try and compensate, but you're releasing lots of lactic acid. That lactic acid is accumulating in your blood, and you're going to breathe heavy to try and pull out CO2 to balance it out, but you're also going to start sliding into an acidic state. So that's a form of metabolic acidosis. If your kidneys aren't working properly and they can't clear away acids, you can't urinate acids out, those acids sit in your blood. That's also a form of metabolic acidosis. Right? Metabolic alkalosis means that you have too much bicarbonate. So it's the same situation. There could be a problem with the kidneys where they're not processing bicarbonate properly, or it could be because you're taking too much of a base into your body. You're consuming too much of a base. And a lot of times that will happen in certain drug overdoses. All right. So acidosis, you want to look at the symptoms next. It doesn't matter if it's respiratory or if it's metabolic. If it's acidosis, you're going to see depression of the central nervous system. So when you think depression, it means it slows it down or it turns it down. Just like when somebody's depressed, they're really slow thinking. Or they're not thinking clearly. They're kind of depressed in mood and depressed in activity, depressed in everything, basically. So when you start turning down the nervous system, what would you think about with thought processes? Are they going to be excited? Are they thinking quick? No, their thoughts going to start slowing down. And you'll start thinking that they might look a little bit more sleepy, they might look a little bit weak, they might look a little tired, they might be easily confused or disoriented, and if it gets too bad, they could slip into a coma, fall asleep completely where you can't wake them out, and then eventually it could lead to death. Because those enzymes are being changed, their neurons are shutting off, and if their neurons shut off going to respiratory muscles, they're gone. So acidosis, you usually see symptoms of depressed activity, so turning down the central nervous system. Alkalosis, just the other, overexcitability of the central nervous system. So a lot of times you'll see numbness, lightheadedness, tingly, nervousness, convulsions, overexcitability. They look a little anxious. You know this because when you're blowing into a balloon, what are you blowing out? You're blowing out lots of CO2. If you're losing CO2, you're losing what? Acid or base? You're losing acids. So your acid level's dropping. What's more dominant in your body if you're losing acid? The base. You're going to a state of alkalosis. So when you're blowing all that CO2 out quickly, you don't just get tired and just want to fall over and go to sleep. You get lightheaded. You get a little bit dizzy. You get tingly. You start getting a little bit anxious, like, whoa, and that feels uncomfortable. So you get this nervous sensation. And then what could happen is, well, probably not with a balloon because you know better than to keep blowing, but with somebody in a massive state of alkalosis, they can start convulsing. And think about it. When you're convulsing, are you having depression of the muscles or overactivity of the muscles? Overactivity. They're excitable. So these are excitable situations. Numbness, lightheadedness, tingly, nervous, convulsions. Then they black out. And then if they're not brought back into a normal pH, then of course that leads to death too. And that, if it goes over 7.8 or 8.0, that's when they're going to die. So those are the two general ideas you want to keep in mind. So here's the big picture. Acidosis causes CNS depression, so depression of activity. Alkalosis causes irritability, excitability, turns things up. So think about how you would compensate with this. If the overall problem is metabolic versus overall problem being respiratory. If it's respiratory, this is easy. If it's respiratory, what organ is dysfunctional? It's the lungs. So what organ has to bring things back into compensation? What organ has to try and fix things because the lungs can't do it? It's the kidney. So you have something called metabolic compensation. If it's metabolic, which means it's the kidney, it's anything else in the body, basically, then the lungs will try and compensate. So let's say somebody has a metabolic acidosis. They're diabetic. What respiratory compensation would you expect? So they're way acidic. They have way too many of these ketone bodies. You should be able to predict that, of course, their kidney's going to try and urinate it out, but the kidneys aren't fast enough. So what are the lungs going to do? they're going to start breathing heavy. They're breathing heavy. They look like they just like ran a marathon. They're breathing. They're trying to catch their breath. They're just like, oh, I feel so winded. Okay? If it's acidosis, what kind of symptoms other than heavy breathing would you see? Would they be excitable, anxious, nervous, lightheaded? No, they're going to be tired, kind of confused. So somebody in diabetic ketone acidosis, they look sleepy. They look kind of lethargic. They look actually kind of like they're drunk. They're not thinking very quickly. They don't answer questions very quickly. They're breathing kind of heavy. So those are just some of the symptoms you want to keep in mind. And the next 4 slides I put together, actually I found the pictures and then combined them so that you could use them as a reference chart. And for some reason it's not changing for me. There it goes. All right, so the first one, metabolic acidosis. And you can see there's your ratio 20:1. So your bicarbonates versus your CO2s, your bases versus your acids. If it's acidosis, you have to think that the acids are becoming more powerful. And it can be more than one way. Either you have too much acid or you have too little base. And in this situation, you can see that the base got lighter, so the acid became dominant. If there's too much CO2, you have to think about how the body will fix it. And it's the lungs, trying to blow it out. Right? The kidneys will try and retain more bases to try and neutralize those, but this is a slower process. Okay? Another thing you can do, and this is beyond this class because this is more when you get into clinical practice, but IVs can actually fix that. Right? So here are some of the signs or symptoms of metabolic acidosis. And this Kussmaul respirations are when people are having these, it looks like they just ran down the street. So they just ran down the street and they're looking at you, just kind of breathing heavy. They may be kind of holding their knees, trying to breathe and panting. That's Kussmaul irritation. Okay. Oops. And then down here are some examples of causes. DKA is diabetic ketone acidosis. Severe diarrhea because they're losing lots of bases. The lower part of your abdominal tract secretes bases, and if you lose them too quick, your body becomes more acidic. Kidney failure or even shock can cause this too. The next one's metabolic alkalosis. So with alkalosis, the base is too dominant. So either the base became real heavy or the acid became too light. And you can see the compensation again. So the kidney's going to try and get rid of more, what? Acid or base. If the base is dominant, it tries to get rid of more of the base. Okay. What's going to happen to breathing? Increased or slower breathing? If you have too many bases and too little acid means you want to slow down your breathing. You're trying to keep the CO2 in. So metabolic alkalosis, you can see the different symptoms. Things like restlessness, okay, heart dysrhythmias, overactivity, tachycardia, again. So overactivity, excitability, anxiousness, nervousness. When you look at respiratory acidosis, you first want to think of what's broken. The lungs. It's respiratory. So the lungs aren't working properly. They're not getting rid of what? CO2. So the CO2 accumulates in the blood, and when you see an accumulation of CO2, you should automatically think an accumulation of acids. So respiratory acidosis. Some causes are things like hypoventilation. They're not breathing very well. And of course, that's going to lead to hypoxia, right? So tissues are going to be deprived of oxygen. Some of the causes you can see down here in the corner. So decreased respiratory stimuli. So when people take anesthetics or drug overdoses, barbiturates will do this too. They slow down the brain, especially what part of the brain stem that would affect breathing. The medulla oblongata. When they slow down the medulla oblongata, the breathing slows down, and if they take too much, then the breathing actually stops. Right? COPD. So they're not getting good at gas exchange. They can't get the CO2 out. Things like emphysema. With emphysema, they can't get proper exchange because, and we haven't talked about this yet, but the alveoli are over-enlarged. So they're big alveoli, but what's interesting is they actually decrease their surface area. So they can't get proper exchange of CO2. Pneumonia, the same situation. So with pneumonia, they're not getting proper CO2 exchange. And then atelectasis, this is when they have fluids build up in the lungs, so they can't get proper exchange again. It's all about the lungs. Next, respiratory alkalosis. So what are they doing? They're breathing too much. They're blowing too much CO2 out. So remember, alkalosis, we want to think increased activity. So irritability, shakiness. So rapid breathing, they're blowing too much air out. There's that tachycardia again, just like we saw with metabolic alkalosis. Lethargy, confusion, they get lightheaded, that tingling. Some of the causes, breathing too much, so anxiety. And this is kind of like a positive feedback loop. They get anxious and they start breathing heavier, which causes that anxious feeling, which makes them breathe heavier. Okay? Mechanical ventilation issues, fear, those things all increase their breathing. So if you look at a review, I put some of these things together, like metabolic acidosis. Right? So metabolic, you want to think it's not the lungs, it's anything else. So it could be the kidneys, it could be because of diabetes. Trying to think of other good examples. Think about how it compensates. So if it's acidosis and the kidneys are going to try and urinate out acid, then what's the lung going to do? The lung's going to try and blow out CO2. Right? If it's metabolic alkalosis, what's going to happen to the breathing? If it's alkalosis, the breathing should slow because they're trying to retain the CO2. And some of the causes, taking too many bases like antacids. So an anti-acid is a base. If you take too much of them, then it can change the pH of the blood. Okay. Excessive vomiting. So they're vomiting up what from their stomach? They're losing acids. If you're losing acid from your body, what becomes more powerful? The base, which is alkalosis. Since it's their stomach that's losing the acid, it's not the lungs, it has to be metabolic. And then reviewing the respiratories. So respiratory acidosis, when they're retaining too much CO2 and things like pneumonia, emphysema, if they take drugs that slow down the nervous system, okay, all of those slow down their breathing or slow down their gas exchange and they retain CO2. If you retain CO2, you retain acids, which makes the acid more powerful. How would the kidney compensate? So here the lung's broken, it has to be the kidney. The kidneys are going to compensate by trying to urinate out more acids. You try and excrete more acids, and you're going to try and keep more bases to balance things out. And then last one, respiratory alkalosis, and I gave you an example of hyperventilation, so anxiety, breathing too fast. Could be a fever, breathing too fast. You're trying to blow out heat. Okay? Hysteria, so another anxiety issue. And because it's the lungs that are at fault here, the kidneys are going to try and fix it by this is actually a typo. It's not increased H ion reabsorption. It's actually an increased bicarbonate excretion. It's going to slow down the loss, but it can't actually reabsorb it. Dang, I hate it when I have a typo in there. And then the last thing is an anion gap. And the anion gap, I'm not going to push this really hard. It's just telling you have to look at all of the anions and the whole blood system, and you're trying to balance things out. Right? Not everything is measured. So for instance, this is what it looks like. You have your cations, your sodium, your potassium. You have some anions like chloride, and what is that? It's bicarbonate, right? There should be a balance. Right? We can measure these things easily, but we usually don't measure other anions, and the other anions are what the anion gap is referring to. Other anions are things like phosphates and sulfates, so we don't measure those directly. When you see an abnormal anion gap is usually when that unmeasured thing is out of balance. Like we don't typically measure ketone bodies or ketone acids. Remember, DK is diabetic ketone acidosis, but ketone bodies, if they start accumulating, you get too much ketone acids, what state are they going to fall into? Then acidosis. Okay. Salicylate, this is actually a derivative of salicylic acid, which you've probably heard of with aspirin or other drugs being in the chemical. But these are things that we don't normally measure. They could be in there. Lactic acidosis, so lactic acid, renal failure, other things that can cause the anion gap. There we go. So kind of a three-step process when you're looking at acid-base balances. So the first thing you want to do is you take an arterial blood gas and you look, is the pH low first? If the pH is low, it's closer to 0, that means they're acidic. It's acidosis. If it's high, it's alkalosis. But do you really know what the cause is? So is it respiratory or metabolic yet? You have no clue. Right? So the next thing you want to look at is you want to look at the CO2 or the bicarbonate. If the CO2 were high, what finger where do you think we'd point our finger? If you had high CO2, we'd probably point right away at the lungs being problematic. Okay, so if it's high CO2, then you can usually go to respiratory, and if it's high CO2, what comes with the high CO2? More acid. So would it be respiratory alkalosis or acidosis? It would be respiratory acidosis. Okay. If the change is primarily in the bicarbonate, then you know it's metabolic. Okay. So if it's a metabolic issue, and the CO2 is normal, that means that the body is actually compensated by changing your breathing. And you'd be able to see that in their breathing. Right, then the last one, look at the value that doesn't correspond to the observed pH change. So if it's not contributing directly to the pH change, and it's inside the normal range, then that means there's no compensation occurring. So if I have high CO2 and then the bicarbonate is normal, that means the lungs are broken and the kidney's not fixed it yet. If I have high CO2 and then you have this partial compensation, which means the kidneys are trying to fix it, it means that the bicarbonate is going to start changing with it. And I put some normal values that you'll see out there in the real world. So pH between 7.35, 7.45. This is your partial pressure, so of oxygen. It should be between 80 and 100 millimeters of mercury. This is not a percent. This is millimeters of mercury. It's a partial pressure. When you're looking at percent, like when you take pulse ox down here, the hemoglobin should be at least 90% saturated. And typically they'll say 95% saturated, but it should be over 90. Do you care about the oxygen as far as pH right now? No, you care about the oxygen as far as whether they have hypoxemia. So are they getting proper exchange of oxygen? Right, and which is kind of an interesting question. Is it possible to have normal oxygen or above 90% oxygen saturation and have an abnormal CO2? It is. We talked about blowing up balloons. If you're blowing up a balloon, you're bringing fresh oxygen in every breath, you get quick exchange. You're going to have high pulse ox, but you're going to have really low CO2 because you're blowing way too much CO2 out. So it's possible to have normal oxygen and an abnormal CO2 at the same time. And this last one, the bicarbonate, HCO3, and you want to keep that between 22 and 26 milliequivalents per liter. And then I put a couple examples in here, and I actually put the answers on it, so I'm not going to go through those for you. So you have the slides at home. You can just walk through and ask yourself this question, and then look at the next slide. So look at, what is this? This is bicarbonate. And then what is this? CO2. And you look at the levels. Are they normal or abnormal? Do they fall within or outside of the normal range? And here are your normals over here. So does the CO2 fall in the right range? Sure doesn't. So the CO2 doesn't fall in the right range. Does this fall in the correct range? Nope. So we've got a problem here. We have metabolic acidosis, and then we have with compensation. What would you expect to see with these people? Are they breathing heavy or breathing weak? They're blowing out a lot of CO2, so they're breathing kind of heavy, right? So you'd answer it with, whoops, thought that was on the next slide. Somewhere here. There it is, metabolic acidosis, and then they are compensating. And again, you can work through these other slides on your own.